Pienso que hay un poco más.
Recording is on.
Voy a compartir mi pantalla.
Ya, y 3 minutos más y empezamos.
Vale, vale. ¿Pueden ver la pantalla?
Yes.
Okay. So I am doing the presentation in English. Is that correct? Since the title is English.
You do whatever you know.
Okay.
I think most people connected are from Ecuador or Yachiatec, so I think you can do it the way you like.
Okay. Thanks.
So I think, Francesc, you are recording the webinar.
Yeah, I'm recording the webinar directly on the Jitsi system. That means that it will come to my Dropbox.
Okay, so later you will be able to share with us, so we can put it in our. We can send the link to the emails for everybody.
Yes.
And we also put all our webinars on YouTube. Is that okay with you?
Okay.
Yeah. It's just that, the webinars from Yachiatec, our professors from Yachiatec, we put them on YouTube later on. So just to make sure it's okay with you.
Okay.
Okay, look, it's 3:05, so we're going to start. First of all, thank you, Francesc, to accept this invitation to share your work. You have been, one of the most productive professor in mathematics in Yachiatec. You have been very successful with the number of publication and the quality of publication. So hopefully we can all learn about your work. And at the end, there will be questions. Everybody needs to put the questions in the chat, and then Francesc can respond to the questions in the order of the chat. Okay? Please make sure you off your microphones. And welcome again, Francesc. Thank you so much.
Thank you very much, Frank. So I will be speaking about recent developments on homotopy continuation based on generalized offsets and computational algebraic geometry. And my subtitle that I put here, and as in the conference, was Make Computational Algebra Great Again. So basically, this is a joint work that has been done together with Fernando Patricio Zapa Camacho, Oscar Vicente Guarnizo Cabezas, and Anthony Sebastian Ramos Cisneros. And I will be also presenting some other examples that have been done with Darka Mioch, Ojeshwa Sharma, and Ali Jamali. And this basically some presentation very close to this, but more focused on the previous research, was done as an invited lecture at the 6th International Conference on Analytical Number Theory and Spatial Tessellations in Kyiv, the capital of Ukraine, from September, took care from September 24th to September 28th, 2018. And the paper that has come from this invited lecture has been recently approved for an AMS MathSciNet indexed paper. So basically, we will see first generalized offsets of quadrics with Routh algorithm. That is an algorithm of polynomial elimination using, of course, the concepts of computational algebraic geometry. Then we will see examples of homotopy continuation and interval analysis. We will see then the barycentric coordinates that are basic for all what is the affine space and affine transformations, and the Voronoi diagram, that is basically a tessellation of the space, of a metric space, into proximal regions. Then we will see the generalized offsets for homotopy continuation, and all this takes place into a project that is to build the Voronoi diagram of Voronoi diagrams of quadrics, and then we'll finally conclude with the discussion. What you have in here is a plot of an offset, of a generalized offset of a quadric. We'll see that later. So first I have to introduce with the basic computational algebraic geometry vocabulary. So first we will introduce the concepts of class, leading variable, and leading monomial of a polynomial. For this, we have to assume that we have a field, and basically the field that we will use in most of the computations will be the field of rational numbers, Q. And then we have to assume that we have a set of variables, x, that is composed of the variables x1 until xn. And then we have the ring of polynomials, k of x, in the variables of x with coefficients in the field k. So basically, a polynomial simply is a linear combination of monomials, where each monomial corresponds to a product of one or more variables, to each one to some power. So if not otherwise stated, the order of the monomials composing a polynomial will be taken as a graded reverse lexicographic monomial ordering, where the constant monomial, 1, is always less than any of the other variables that are x1 and then x2 until xn. So we'll have all the monomials sorted with the graded reverse lexicographic monomial ordering. So that means that if two monomials have the same degree, then we will order them according to the reverse lexicographic monomial order. Here we have what we call the universal field over the field K. That is simply the any projective space over an algebraically closed field. Because, of course, the results of algebraic geometry are only valid for algebraically closed fields, like the field of complex numbers. So, first definition, class. If P is a polynomial of the ring of polynomials in the variables of the set X and the coefficients in the set K, in the field K, the class of P, denoted by CLS of P, is the C, the index C, such that XC is the largest variable that occurs in P. So for example, if I have a polynomial that has the monomial xn, in this case, it would be, the class of P would be n. So if class of P equals C, then XC is called the leading variable and denoted by L var of P. The highest degree monomial of P as a univariate polynomial in the leading variable of P is called the leading monomial. And its coefficient is called the initial of P and denoted by init of P. So, of course, I can give you an example of this. Let me check if it works. No. I will give examples later. So what we call a variety, basically for a given set of polynomials, a calligraphic P, that is a subset of the ring of polynomials in the variables of the set X with coefficients in the field K, this is called 0 of P, is the set of points of the universal field such that for any polynomial in the polynomial set P, P of X is equal to 0. And this is called variety. So for a set of polynomials P and a polynomial D, we define the 0 of P such that D is not 0. So I mean, basically what we are doing is the subtraction of the variety of P minus the variety of D. Okay, so there's 0 of P minus 0 of D, and this is called the quasi-algebraic variety. Now, ordering, a polynomial P1 has higher ordering than a polynomial P2, denoted as P2 less than P1, if either the class of P1 is greater than the class of P2, or they have the same class, C, and the degree of P1 in XC is greater than the degree of P2 in XC, where, of course, deg is the degree of the polynomial. If none of the polynomials has higher ordering than the other, they are said to have the same rank, and then we have this notation in here. Okay? So triangular set, basically, a polynomial Q is reduced with respect to P if the class of P equals C is greater than 0, and the degree of Q in XC, that is the variable of the class, is less than the degree of P in XC. A sequence of non-zero polynomials A, that is formed by A1, A2 until AR, is a triangular set if either R equals 1, that means there is only one polynomial, or the class of A1 is less than the class of A2, is less than the class of A3 up to the class of AR. A triangular set is called an ascending chain, or simply a chain, if each one of the AJ, the polynomials AJ, is reduced with respect to AI for I less than J. That means that the next polynomials in the ascending chains are all reduced with respect to the earlier polynomials. And what does that mean that they are reduced? That means that the remainder of the Euclidean division by the polynomial AJ, of the polynomial AJ by all the polynomials A1 until AJ minus 1 is 0. For a chain A, we denote by IA the product of all the initials of the polynomials in A. The initials of the polynomials are the leading coefficients. The ascending chain, so if we have A prime that is an ascending chain with the A prime i's, and A double prime that is an ascending chain with the A double prime i's, A prime is said to be of lower ordering than A double prime if there exists some K such that A prime 1 is of the same ordering as A double prime 1 until A prime K minus 1 is of the same ordering of A double prime K minus 1, while A prime K is of less ordering than A double prime K, or the number of polynomials in the chain A prime is greater than the number of polynomials in the chain A double prime. And all these AI's from 1 to R double prime, they have the same ordering. So a sequence of ascending chains steadily lower in ordering is finite. You cannot have an infinite chain, an infinite ascending chain. Okay. A basic set of a polynomial set P is any chain of lowest ordering containing P. A polynomial Q is called reduced with respect to a chain A. If Q is reduced with respect to all the polynomials in A, that means that the remainder of the Euclidean division with respect to all the polynomials in the chain A is always 0. Let A be a basic set of polynomial set P. If P is reduced with respect to A, then a basic set of the union of the polynomial set P and the only polynomial P is of lower ordering than that of the polynomial set P. That means when we add polynomials, we will be getting lower ordering chains. So the Routh algorithm, basically, what it does is that it starts with two polynomials, f and g, with c being the class of f and I being the initial of f. And either g is reduced with respect to f, which means that the degree of g in xc is less than the degree of f in xc, or the degree of g in xc is greater than or equal to the degree of f and xc, and then it is possible to divide by the Euclidean division algorithm the polynomial g by the polynomial f as univariate polynomials in xc. And here, the normal Routh algorithm uses the pseudo-reminder. But I'm not using the pseudo-reminder because the pseudo-reminder can introduce unwishable factors. That means that we can get extra factors in the polynomials that we get by the Routh algorithm. So instead of Routh algorithm that uses the pseudo-reminder that is described here, I'm using the S polynomial that is used in the computations of the Grobner basis by Bruno Buchberger. So I will not go in more details. And basically what we have is that we will be adding in my case, all the S polynomials of the polynomials that form basically a set of polynomials, a polynomial set. So we take the first polynomial of the polynomial set, and then we take the second polynomial of the polynomial set. But we have to maintain that basically we will be having a chain. That means that the class of the polynomials will be changing. And basically, this S polynomial, what it does is that it allows you to eliminate one variable, that is the variable of the class, from two polynomials. Okay? And more generally, by repeated application of the S polynomial, you can eliminate n-1 variables from n algebraically independent polynomials. And then we will arrive to what is called a characteristic set. So now, application to the generalized offset of a quadric. Now, we will take a quadric, that means an algebraic variety that is defined by a second-degree polynomial of the form ax squared plus bxy plus cxz plus dy squared plus eyz plus fz squared plus gx plus hy plus iz plus j. Okay, and in here I'm already placing the monomial. The monomials are x squared, xy, xz, y squared, yz, z squared, x, y, z, and 1. And basically, a polynomial that is such that the polynomial that defines a quadric is a linear combination of monomials where each one of the monomials is multiplied by a number that belongs to the field K. Okay? And then, in order to speak about the generalized offset, basically, I need to define the parametric equation of the normal to the quadric. For this, I have these three equations, okay? So in this x, y, z in lowercase are the coordinates of a point on the quadric Q. And uppercase x, uppercase y, uppercase z are the coordinates of a point on the generalized offset to that quadric of offset parameter O, lowercase o, okay? So I have the three equations that define the normal. And basically, these are parametric equations, so they depend on the parameter lambda. You know that basically the normal vector to the quadric, at the point of a quadric, corresponds to the gradient of the implicit function f of x, y, z that is given by this second-degree polynomial in x, y, and z. So that means that here you have the partial derivative of this polynomial f with respect to x, that is 2ax plus by plus cz plus g. Then you have the partial derivative of this polynomial with respect to y, that is bx plus 2 dy plus ez plus h. And then you have the partial derivative of this polynomial f with respect to the z variable, that is cx for here, plus EY for here, plus 2FZ for here, and plus I. Okay, and finally, you express that the square distance between the point on the quadric and the point on the ellipse, on the offset, sorry, on the generalized offset to the quadric, is exactly the square of the offset parameter. If you have any questions, please feel free to interrupt me at this level because we are doing this example. No? Any question? Okay. So basically, what we will be doing with the Routh algorithm is that we will compute basically the S polynomials of each one of the polynomials of higher degree by the polynomials of lower degree. Here, the degree of this polynomial is 2, but the degree of this polynomial is 1. Well, it depends if we consider in x, y, and z, but in each one of the classes x, y, and z, the degree of this polynomial is 1. The degree of the polynomial in x, y, and z for this polynomial is 1. The degree of this polynomial in x, y, or z is 1. Okay. So basically, what we'll do is we will do the S polynomial of this polynomial by this one, this polynomial by this one, this polynomial by this one, and also this one by this one, because this has degree 2 with respect to x, y, and z. Okay. And basically, what we will do is that we'll look at the reminders that are obtained by this S polynomial function, and we will still be dividing as much as we can until we eliminate first the x, then the y, then the z, and finally the lambda. Okay? So that means that once we will have eliminated the x, y, and z, we will not have anymore the coordinates of the point on the quadric. We will only have the coordinates of the new point on the offset, that is x uppercase x, uppercase y, uppercase z, and the lambda parameter. Okay? So basically, what we will be doing is solving a system of 5 equations in 4 unknowns that are lowercase x, lowercase y, lowercase z that correspond to the point on the quadric, and lambda that corresponds to the basically the parameter on the normal. Okay? So by computing the characteristic set using Routh algorithm, but in fact a little bit modified Routh algorithm that uses the S polynomial instead of the pseudo reminder, we obtain at the different steps the formal coefficients corresponding to geometric, topological, and geometric topology invariants of the generalized offset of quadrics. You can look at the files that are available on this Google Drive location, and basically each one of the files has a number at the end that corresponds to the step, because this is an iterative algorithm. We start by taking the first step of pseudo reminders of S polynomials, and then we will replace each one of the new coefficients by another simple coefficient. Okay, and then we'll repeat this operation and we will get basically what we want. So we will get algebraic combinations that are also called syzygies of the formal coefficients defining the quadrics, that are the A, B, C, D, E, F, G, H, I, and J. The first invariants are those coefficients of the monomials of total degree 2 that correspond to the quadratic forms that define the quadrics. And these coefficients define the classification of quadrics into reducible components. So basically, you know that if you take the equation of a plane of the form ax plus by plus cz plus d equals 0, and if you multiply together 2 equations of planes, you will get a quadric. and this quadric is reducible. Okay, but in general, the other quadrics, especially the ellipsoids, the paraboloids, the hyperboloids, they are not reducible. But basically, you will be able to get a classification of quadrics into reducible quadrics and irreducible quadrics. So basically, you will get all the invariants that correspond to basically some of the coefficients of the normal that correspond to the polynomials 2ax plus by plus cz plus g, or bx plus 2dy plus ez plus h, or cx plus ey plus 2fz plus I are equal to 0. And this corresponds to basically special configurations of normals to the quadric that are obtained, contained in planes of equations lowercase x equals uppercase x, lowercase y equals uppercase y, and lowercase z equals uppercase z. I will not go too much into this, but basically you can get by this process all the invariants, either geometric or topological or of geometric topology of the problem at hand. That is the offset, the generalized offset. Because of course the offset is not an algebraic variety in general, but the generalized offset is an algebraic variety. That means it's defined by polynomials, the polynomials that we have seen in the case of quadrics. So I will go to the application. There has been computations that have been taking 3 months on the Kinde supercomputer. This is the aerial photograph of the installations of the Kinde supercomputer, now on the almost vertical projection, and the interior of the Kinde supercomputer, and basically zoom at the interior of the IBM SL822 nodes of the Kinde supercomputer. And of course, this is the internal organization of the Kinde supercomputer, and I will not go into that detail. And basically, the result is the application of Routh algorithm for obtaining the generalized offset of quadrics. In this case, we have a quadric, that is the quadric that corresponds to the variety defined by the only polynomial -4 plus 4x plus x squared minus 3y plus xy plus y squared minus 2z plus 2xz plus 3yz plus z squared. And the offset parameter O is equal to 3. And we get this basically offset. The original variety is here with this orange color. And then the offset is in gray with two irreducible components. And here another example of offset for another algebraic variety that corresponds to this algebraic variety. And here there is one part that we see outside, one part inside. Here for this part we see only the external part and not the internal part of the offset. Here the quadric is defined by the second degree polynomial 1 plus 2x squared plus 2y plus 3yz plus 2z squared. Now, the motivation for homotopy continuation of interval valued functions of interval vectors is that our real world is continuous, not discrete in most of the places. Of course, if you are in a place where there is a war, then of course nothing is continuous. And of course, the physical phenomena in general, except in these war zones, they are almost everywhere continuous. Now, interval analysis, homotopies, and Dirichlet tessellations are used for modeling physical phenomena with their uncertainty. And when I'm saying physical, it can be also chemical, or it could be biological. Now, we can do 2D, 3D, 4D, ND reconstruction from any images, okay? And when I'm saying images, it's not restricted to color images. It can be multi-beam echo sounder images. It can be computer tomography images. It can be radar images. It can be anything using homotopies and level sets. We have applied all this technology to, all this methodology to consume power and emitted radiation emulation for handheld devices using interval valued homotopies. And this gave rise to a patent with Nokia. We have potential applications of new abstract cell complex compact data structure that is the most compact geometric topology and data structure to real-world data analysis. And basically, all this obeys to the class of problems that is the reconstruction problems. We want to reconstruct a function inside some domain. And of course, this domain is a domain of some higher dimensional topological uniform or metric space. This can be done through point cross-sections or point clouds. It can be done through linear cross-sections. That means sections with a linear subspace, like a plane or line, and or planar cross-sections. Okay. So now, basically, we have this kind of problems in acoustic analysis. It can be also in marine surveys. It can be also in modeling of physical phenomena. Or when I'm saying physical, it can be also chemical, or it can be biological. When one tries to reconstruct a vector or real valued function of several variables. So now the interval analysis is the analogous to the real analysis, where we replace real numbers like a in here with real intervals. That means the interval bounded by the lower bound of the interval, that is here, and the upper bound of the interval. And Ramon Moore, who is the founder of interval analysis, defined interval analysis as the unified approach to the machine determination of an approximate solution and the bound on its total computational error, roundoff, truncation, and propagation of the initial error by a single computation. So, a geometric illustration of interval analysis. We want to approximate functions. Here, it's a function of one variable that has a real value, and we want to subdivide basically in intervals the input interval into subintervals until we will be sure that we control the uncertainty of the graph of the function within some tolerance of the perfect function evaluation. Here is an example where basically we have a series of observations. Each one of these rectangles corresponds to the Cartesian product of an interval in the x variable, that is the transmitted power, and in y we have the consumed power. Okay, and then the Cartesian product of the interval in x and the interval in y gives us an interval rectangle. Of course, I assume that you all know what is this. This is the illustration of the Newton method for finding a root of a function, and we have the analogous to the Newton method in interval analysis. The only difference is that, of course, instead of having a single tangent, we have a tangent cone that corresponds to the uncertainty of the tangent. That corresponds to the uncertainty of the first derivative. We have then application to the 2D, 3D, 4D, and ND reconstruction from any kind of images. So here is the case of acoustic signals, but I will go very fast from here. We have different kinds of geometries, either 2D geometry or 3D geometries. Here you have the fish, all the fishes that correspond to the highest levels of intensity. You have the bottom of the aquarium in which we did this experiment, and we have all these that are bubbles of air. Then we could have also geometries in 3D, like in the case of computer tomography. And basically, we have a 3D image, an example of 3D image. And basically, we have the main challenges that are the noise, the speckle and the artifacts, the changing and arbitrary topology, the fact that a big fish can eat a small fish, and the huge amount of data. In one afternoon in the Oceanographic Museum of Hirtshals in the north of Jutland in Denmark, we collected several terabytes of data. So we have different kinds of methodologies. We have volume segmentation. We have reconstruction from ordered intersections. That means intersections at regular intervals between the planes, intersection planes. And we can have also reconstruction from arbitrary intersections. I will go to show examples. Here are volumetric images, and they come from different fields. And we have used level set methods. I will not go into this. And basically an example of application of the level set method in the case of the acoustic images of fishes. Of course, what we are interested in is the objects that with the highest intensity. Basically, we have a multi-phase segmentation methods that correspond to identifying different kind of objects like the fishes, the water bubbles, and the sea floor or the floor of the aquarium. I will go very fast on this because time is running. We can use CUDA-based solvers. We can increase the performance of the computations using the computer unified device architecture, CUDA, using grids of blocks of threads. Application in the case of fishes, what we will get in the case of 3D images are the trajectories of the fishes. We can do the segmentation of the human thoracic cage, or segmentations of viruses and etc. We can apply the Hausdorff distance measure between the two surfaces, the original one and the reconstructed one, to be able to see what is the accuracy of the reconstruction. And here are some examples by introducing noise. So what we see is that when the noise is being multiplied, then the Hausdorff distance is not multiplied by the same proportion, very little. So that means that the reconstruction is very stable with respect to the noise. We can look at the speed up of the different portions of the reconstruction. Here, the OpenMP speed up. And basically, here comes to the presentation of what is a homotopy. A homotopy is a continuous deformation of a function. So if we take the green graph that corresponds to, this graph here is the graph of this function that is called f0 of x. It's also called the initial map. And the red graph corresponds to the graph of the function f1 of x that corresponds to the terminal map. Then we have the continuous deformation of the green graph into the red graph. Okay, this deformation is continuous. And this is basically the illustration of homotopy. Of course, the mathematical definition of homotopy is that we need to consider two different functions, f0 and f1, from a topological space X to a topological space Y. That is defined as a continuous map H from the Cartesian product of the topological space X by the unit interval 0, 1 into the topological space Y, such that H of x0 is equal to f0 and H of x1 is equal to f1, where X belongs to the topological space X. Lowercase x belongs to the topological space X. The second parameter of H is also called the homotopy parameter, and it's called lambda in general. And it allows for a continuous deformation of f0 to f1. And the use of continuous deformations was typically for solving systems of difficult equations, and basically changing a system of difficult equations, difficult meaning that it's very hard or impossible to solve them analytically, into another system for which an analytical solution is possible. Apply this to homotopy reconstruction. Basically, we assume that we know some variable along some beam, okay? And then basically what we will have is that we will have a field of homotopies. That means not one homotopy, but one homotopy in between each one of the consecutive beams, okay? I will give an example. We have different kinds of homotopies. We have linear homotopy, where basically the homotopy function is a convex combination of the two functions. It's only 0 times continuously differentiable. It's local and it's shape preserving. Or we can have non-linear homotopies that corresponds to homotopy that is polynomial. So it is in the realm of algebraic geometry. And basically, in this case, we have the degree -1 times continuously differentiable. It's local, but we have staircase effect. And the cubic spline homotopies, they are global, they are not natural, but they are twice continuously differentiable. And finally, the shape-preserving homotopies that we introduced together with Ojeswa Sharma are 2 times continuously differentiable in between the beams, and only 1 time continuously differentiable at the beams. They are global and they are shape-preserving. So these are the linear homotopies, that is to say a convex combination of the 2 functions. In here, it will not be f0 and f1, but it will be fj and fj plus 1 because we have a homotopy field. So this is the homotopy hj. The parameter lambda corresponds to the relative angular position in between the 2 beams. Linear homotopy, what we have is C0 only. And then we have basically this kind of ugly behavior. That means that we have basically a straight line junction between the beams. Non-linear homotopy, basically what we have is what we have when the nu is the exponent, then it is nu -1 times continuously differentiable. The effect on the reconstruction is when we have powers that are very big. Well, power 1 is the linear case, power 0.5 is this, power 1.52, and then we will arrive to what we call the staircase effect in the case, for example, in here of 50, something that is really ugly. Cubic spline homotopies, I will go on and on. Basically, this is a cubic spline homotopy. The problem of cubic spline homotopies is that they introduce changes in the monotonicity of the functions. And for this, we used shape-preserving homotopy. That means we this is the result of a cubic spline with the spikes of the cubic polynomial that corresponds to cubic spline. And instead of this cubic polynomial, we will use the Hermite basis functions. And we will use these Hermite basis functions to express the homotopy. And this will arrive to something that is shape-preserving. That means the monotonicity of the function, of the original function, is respected. These are some results with the linear, non-linear, cubic spline with all its characteristic spikes, and the shape-preserving homotopy. The reconstruction accuracy with the Hausdorff distance, and also the ratio of the area of the reconstruction and the area of the original surface, and the volume of the original bounded domain and the volume of the reconstructed bounded domain. A comparison with the radial basis functions reconstruction and homotopy reconstruction. Of course, radial basis functions can give very ugly results like this one. And the homotopy reconstruction can give smoother results. And we have what we call the critical points that correspond to the topological analysis of the shape of the objects. I will not go into that. We place phantoms into the aquarium, and we made the reconstruction, and we got the different kinds of reconstructions for the different objects. I will come to another kind of problems, that is reconstructing an object in the plane from arbitrary cross-sections with lines. And here we define a multiple variable homotopy with n homotopy parameters instead of 1 homotopy parameters. And this is what we will use for the reconstruction of some physical or chemical or biological value in between quadrics. So we have a reconstruction. Basically, I will not go into the mathematics because, well, I will go into the picture. So basically what we do is that we use barycentric coordinates. So barycentric coordinates are used to position a point inside the polygon. Okay. And basically in here, what we'll do is that we'll consider for an interpolation point P, the orthogonal distance of P with respect to the edge of a polygon. But in general, what we want is not interpolating inside a planar polygon. We want to interpolate in a volume that is located in between quadrics. So basically, the lambda parameter will be, in the case of a Voronoi diagram, the area stolen to the neighboring object divided by the sum of the area stolen to the neighboring objects. So this is an example. If I want to interpolate a physical or biological or chemical value variable in this point, I will not need to introduce this point, but I will need to compute which are the areas that this point would steal to its neighbors if it was introduced inside the Voronoi diagram. For this, we don't need to compute the Voronoi diagram with this new point, but we need to compute the Voronoi diagram of all these edges that corresponds to these dash edges here, dash edges, and we need to compute what would be the area that would be stolen by this point to this edge, this edge. In this edge, it doesn't steal anything. This edge and this edge doesn't steal anything. So basically, the homotopy formulation is that we have a function on each one of these edges, okay? And we interpolate the function at this point by knowing what is the lambda parameter and the orthogonal distance of this point with respect to each one of these edges, and evaluating the beam function at the level of this distance. So basically, what we will get is something that is at least one time continuously differentiable. Here is an example. We have basically an original object, and we made some intersections with some linear subspaces of dimension 1 in here, some infinite straight lines. And then we get a first reconstruction that corresponds to this, okay? And then we will apply some rotations. This is another case with the Voronoi, and this is with the orthogonal distance and Voronoi. And basically, we have a sampling condition that is based on the concept that is called the tortuosity. I will not enter into this. It's defining here. And we are looking at the reconstruction accuracy. That means the length of the boundary of the bonding curve in here, the ratio of the lengths of the bonding curves, and the ratio of the areas of the surfaces. So these are examples with different number of lines. And we compared our method with the method of Mémary and Jean-Daniel Boissonnat. And we got better results with our homotopies than with the work of Mémary and Boissonnat. I will not go into this. We can use smooth rotations, and then we will get a better reconstruction. I will go into what is interesting for me. Well, we applied this to other problems, not only reconstruction of fishes, but also reconstruction of the power consumed by a device that has a model. So now here, the generalized offset for homotopy continuation. So basically, what we will have is that the homotopy continuation based on quadrics corresponds to the homotopy parameter lambda being the offset distance, OI, of the interpolation point with respect to each one of the neighboring quadrics over the sum of the offsets to the neighboring quadrics. And this realizes the partition of unity. This is clearly the application of the barycentric coordinates that we have seen earlier, and they are used in homotopy continuation that we have seen earlier. Each quadric enclosing the interpolation point has associated an edge map, Fi of x, y, and z, of the coordinates x, y, z of this interpolation point. The homotopy continuation computes the closest point of each one of the enclosing quadrics, Pi of x, y, z, from the interpolating point x, y, and z, and the orthogonal corresponds to the smallest distances in which we are solving for the O parameter, given the xyz coordinates of the point on the quadric and the uppercase xyz coordinates on the point on the offset. That corresponds to the interpolating point. And then basically we apply this to the computation of the lambdas that corresponds to the offset, not the offset parameter, but the real offset distance. That means the offset that would be the real offset of x, y, and z divided by the sum of the other offsets of the neighboring quadrics. In this case, there are s quadrics, and each one of these parameters goes from 0 to s minus 1. And then we apply the homotopy reconstruction, that is the summation from I equals to 0 to s minus 1 of lambda I, that is computed here, multiplied by fi of x, y, z, that corresponds to the functions that we know on each one of these quadrics. The significance of all this is that we use Voronoi tessellations, we use homotopy continuation, we use interval analysis as effective mathematical tools to solve a class of reconstruction problems. We got new algorithms for reconstruction from linear or planar or n-1 dimensional cross-sections that corresponds to the setup of photogrammetry. It handles arbitrary geometry and topology. We have introduced a new type of edge-based barycentric coordinates associated with generalized Voronoi tessellations. And we have an application to reconstruction problems in acoustic imaging, biomedical imaging, and smartphone design. And we use the CPU, GPU acceleration over all the computations as a complete pipeline. And the applicability of all this, why it is important, because many surfaces can be approximated by quadrics, including common furniture or less common curved buildings or trajectories of planets. We can know some physical, chemical, biological, or other kinds of spatially distributed variables on these quadrics, and we wish to interpolate such variables in the regions bounded by such quadrics. And we will use homotopy continuation for interpolating such regions using the minimum distance of the interpolation point to the neighboring quadrics that can be obtained by resolving the offset parameter from the equation of the quadric and the position of the interpolation point. And basically, this is all. Thank you to Professor Alina Sita and all the other members of the organizing committee of the International Conference on Analytic Number Theory and Spatial Tessellations for the invitation and the excellent organization, and all of you for your attention. Thank you very much. Here are the references.
Francesc.
Yes.
So, we have a group. So I believe we can maybe ask you questions without
Sure.
writing. You
Yeah.
just need to raise your hand. Okay, if you want to ask a question. Well, first of all, I want to congratulate you, Francesc. I don't go too much in. I'm not very familiar with the research in mathematics and TICS, but it looks like your research is very applied. And it also looks like you have a lot of collaboration. These two things make it unique and helps you to have high quality publications. Or what is you are a very experienced professor. What kind of advice you could give to students or to junior professors to kind of have the chance to, improve the quality? The application is critical, or the collaboration, or both?
Well, if I have an advice for anybody in any scientific discipline, is to learn as many mathematics as you can, because this you will always find a way to apply them in some problem. So this is the first thing. For me, mathematics is central to anything. Okay, it's central to engineering disciplines, it's central to scientific disciplines, it's central to all the data analysis that are used in social sciences and economical sciences. So this is something that is basically a toolkit. You have a toolkit that is called mathematics. And it's not for nothing that a lot of education systems in the past have used mathematics as their main selection process. I don't say that it's always good, the ways how they use mathematics to select people. For example, in France, if you have done a baccalaureate C, that is a Bachelor of Mathematics and Physical Sciences, you have priority including to entering, or you had priority including to entering into the Hippocagne preparatory classes to the literary Grandes Écoles. So, of course, for me, somebody who can do mathematics can do abstraction. And abstraction is key in many different processes. So, of course, my main advice is to learn as many mathematics as you can. Then, of course, the application is important. There are a lot of colleagues in computational geometry or in algebraic geometry that are not interested in the applicability of their tools, okay? And this is a problem because, of course, in my career, I have benefited from industrial PhD scholarships. Joshua Sharma was an industrial PhD student who was financed by the Danish Agency of Science, Technology and Innovation and the Nokia company in Denmark. But of course, the decision of accepting this research project was taken by Nokia in Finland. And of course, I had other applications, like, for example, I got a European Union Eureka Eurostars grant, because I have been in contact with two companies, one in Denmark and one in Spain, and we proposed a common project to get some money, some research money. And of course, so it's important to have contacts, of course. So of course, the contacts you can gain them through conferences, but in my case, well, it happened that I had a PhD, well, first a master student who wanted to do his thesis with me, who was Deogracius Musige, who did his thesis with Nokia. And then it's how I met Vincent Lolanier, who was his master supervisor at Nokia. And then we proposed the industrial PhD grant application to Vincent Lolanier, and then he transmitted this to his direction in Copenhagen, and then it went from Copenhagen to Helsinki, to Nokia Finland. So of course it's important to have a lot of contacts, and it's important to have a lot of mathematics, but it's also important to try yourself. What happened in the case of the Spanish company is that I was watching a program about innovation on the Spanish public TV, Televisión Española, one weekend when I was in Spain, and this company presented what they were doing about mapping tablet. And then I contacted them, and then I proposed them to do this grant application. So it's also, you have to try to get contacts. They will not come only through conferences.
Thank you, Francesc. Look, Israel is here, right? Are you still here, Israel?
Yeah.
First of all,
yes, I am.
Hey, Israel, I'm surprised that there are so little professors from mathematics or TICS that joined this webinar. I don't believe that all of them have class at this time. And, I think we are missing the point of these webinars. There are two people from mathematics that represent, Francesc and Hugo. They have a very good reason for this. They are people who have published 5, 6, 10 Scopus Q1. So basically, they know what they are doing. And the professors don't join these webinars. I am surprised. What is your opinion, Israel?
Well, sadly, I do not have an answer for that, Frank. I think that we should encourage these kind of activities and try to do this as much as possible. Actually, last year, at the beginning of this year, when we did some seminars at school, I mentioned to Francis, and I said that people who publish more should do this kind of activities more, because simply you have more to say, right? So actually, for me, it's very nice to see this presentation. I've been learning a lot, and yeah, hopefully this thing is something that will keep going on. Not only now because of the situation, but in general, we have to meet and talk with each other. But sadly, Frank, I do not have an answer for why are other professors not here. It's also a mystery to me.
But you see as well, here's an example of a professor, and actually Hugo is the same. He's a professor who collaborates a lot, you know, and the result is the publication. I have been to some of the mathematics presentation in December, and no collaboration. Just one professor sitting in the table and solving some equations, and that's it. But it seems that collaboration is also very important in your field, in mathematics and in TICS. Do you agree with this, or is there something that we have to do with the school that you as a coordinator with the dean can do?
Well, I agree that collaboration is important. I think that we should encourage that, and probably we should try to convey this idea to other people. But I think that more or less everybody understands that. But I think that we have to see some evidence of that, and maybe we should try to be more, to put a little more emphasis on this with other professors.
Excellent. Well, I will stop to talk. I think there are two. There are two questions. No, there. Well, basically, TT has a.
Sorry, yes, I'm looking at it. Yeah, okay. Okay. I don't know if you know something called the molecular dynamics. Basically, it is the study of the movement of atoms. Yes, molecules over time. I did not know about what is exactly an homotopy, but I feel it is basically the deformation of a function. Yes, I guess it is, but it's a continuous deformation of a function. So, of course, you cannot do a non-continuous deformation of a function. Or better said, you can do it, but you will have to basically segment the non-continuous parts of the deformation and use another algebraic geometry tool that is called the blow-up. A blow-up, basically, it's an explosion. When you have a bomb, okay, that explodes, then every particle tries to get away from the bomb, from the center of a bomb, okay? So, okay, the formation function, I guess it is the mathematical basis of molecular dynamics, yeah? Do you think my intuition is right to think homotopy is the mathematical foundation of all? Yeah, well, basically, how you define your molecular dynamics is the movement of atoms over time. And of course, you can have different kinds of behaviors. You can have continuous movements of atoms. That means that if you don't have an atom that will be splitting into two atoms, for example, in the atomic centrals, in the nuclear energy centrums, what you have is that you have a nucleus that is bombarding another one, and then this one is getting multiplied, and then there is a lot of energy. And you have also the nuclear fusion, where you have basically a change in the topology. So as long as you have a change of topology, you are out of homotopy continuation. But the change of topology, you can get it with the algebraic geometry blow-up. Okay, so with all this, you can say that it's not only homotopy that is the mathematical basis of molecular dynamics, it's algebraic geometry that is the basis of mathematical, or the mathematical basis of molecular dynamics. And do you think my intuition is right to think that, okay, there are different algorithms used, and one of them is predictor corrector. Yes, this is one of the homotopy algorithms. Yes, and we use it. No problem. No, yes, fine. Yeah, that's very nice. And what I wanted to say is that this algebraic geometry is also something that can be applied to very different things. And for this, I would like to share my screen. I will just take a few moments for this. I have applied algebraic geometry to the case of the modeling of the evolution of the cases of the coronavirus. So basically, I will just get this on my computer. Is it okay? Yeah. Yeah. Okay. So basically, I will just sorry. I will open something else that is ePDF viewer, and I will open my documents. Okay, no, I can't. What I will do is that I will change the sharing of the screen where I am. Yeah, I will change the screen, and basically here what you see is the evolution in these lines that are basically a sequence of straight line segments. You have the blue straight line segment that corresponds to the number of active cases of coronavirus in the Principality of Andorra. And then what you have in red is this number minus that minus the uncertainty that is basically the uncertainty of the tests of the coronavirus, and this is the number of observations of active cases plus the uncertainty. And then starting from basically the behavior from day 0 to day 20, where basically we had this improvement of the situation, because instead of having an exponential behavior, we had a linear behavior. Then I made an extrapolation from what happened in these first 20 days. And then this gave me 3 curves. A curve that corresponds to the algebraic interpolation, not interpolation, but in this case, extrapolation. I interpolated all what was between day 0 and day 20, and then I extrapolated to the remainder. And basically have a median curve plus or minus uncertainty. Okay, so this is an example of application of algebraic geometry. And of course, to come back to your question, everything in physics, in chemistry, in biology, in socio-economic data analysis can be done using algebraic geometry.
Hey, Francesc, this is very interesting. Are you planning to publish your work on this, or?
Yeah, but I have to get some more data. I have to get some more data of other epidemia to be able to prove my proof of concept, because of course
Okay.
I interpolated on the first 20 days, and then I extrapolated on the remainder. But of course, I have to try to do it on other epidemia, but I don't have
Okay.
data. That's the problem. I tried to get data, but I didn't get data yet.
I mean, this is exactly what Tech need to do in the School of Mathematics and TICS, using the tools for applications. Of course, we need to have basic science. I understand all that, but up to a point. And I would wish that more professors are in this direction a little bit, but maybe it's because I don't know.
Well, for me, I see algebraic geometry everywhere, because basically the Weierstrass approximation theorem tells you that the set of polynomial functions is dense in the set of continuous functions. And then the Kolmogorov theorem tells you that any function of n variables that is continuous can be expressed as a summation of continuous functions of only one variable. That is to say, a continuous function of n variables can be written as a linear combination of several functions of only one variable. And if you take these two things together, then a lot of things in the world are in the domain of algebraic geometry, because except if you are in a country like Syria or other countries that are in war, almost everything is continuous. It's not every time that you break an object. When you break an object, then you don't have any more continuity. But as long as you don't break an object, you are in the continuous realm. And algebraic geometry allows you to combine the homotopy continuation for the continuous domains with the blow-up of algebraic geometry that corresponds to the how you can change the affine space of points into the projective space. The projective space is the set of infinite straight lines through the origin. This is the mathematical basis of computer graphics, of computer vision, of photogrammetry. And basically the common language of all this is mathematics. It is the homogeneous coordinates of the projective space that are a particular case of the Plucker coordinates of the Grassmann varieties that corresponds to all the sublinear sub-vector spaces of a given vector space. So to conclude, mathematics is the universal language. And algebraic geometry and algebraic topology and algebraic geometric topology are very good tools for this language, that is also a lot of tools.
Okay, excellent. I don't know if there is we have time. Well, actually, yeah, maybe time for one more question, just a quick one if there is. Okay, I don't see new questions, Francesc. I think everybody knows you, where to find you.
Mm-hmm.
Thank you so much to share this really nice research. You know, I know you since arriving at Tech, but really I was not sure what you're doing. I'm glad that we do this kind of webinars, and I think we will continue even after this quarantine. I think it's a good way to share what we are doing. Thank you, everybody, to join the webinar. Thank you, Francesc. Everybody stay safe. Stay safe.
Thank you very much to all of you.
Bye-bye.
Bye.